Hey all listeners, let's see this question of Irodov, question of hydrodynamics. Question number is 1.324. It's a very good question of the pressure difference. So let's see the question. The question is saying a horizontally oriented tube AB, this tube AB of length L, rotates with a constant angular velocity omega about a stationary vertical axis O dash, passing through the end A. Suppose if this question had come in the JEE main also. So if this is some liquid is there and if it rotates like that, so because of the centrifugal force, liquid will go towards the right hand. There will not be any normal here, and it will push the wall. So the tendency of the liquid will be to go away, and there is a small orifice. So from that orifice it will ooze out. So that's what it is talking about. So the tube is filled with an ideal fluid. The end A of the tube is open. So this end A is open. So here the pressure would be P ATM up to here. And end B has a very small orifice. Find the velocity of the fluid relative to the tube as a function of the column height h. So basically, with respect to container itself, it is a moving liquid because this liquid is coming out. So this end will also be moving. So in addition to centrifugal force, there would be a Coriolis force also, but we are going to neglect it because the orifice is very small. So orifice is very small, so practically this will move with a very small velocity. So with respect to this tube, we will assume this part of liquid to be static liquid. Then we can apply Bernoulli theorem from here to here between any 2 points. All right. But before that, I want to derive an expression for the pressure difference along length, and that is important result also, and that result will also be used in some question also. In fact, in a later question that is asked to derive, but for here I'll derive. So for a rotating container which is axis of rotation is vertical. So first of all, let me get that expression. Suppose we have this container, and in this container is rotating uniformly with some angular velocity omega. So with respect to container, the liquid is at rest, so liquid will also be rotating. All right. We are looking everything with respect to the container. So we know that in this case the liquid takes the paraboloid of revolution shape. I'm not interested in the parabola part. I'm interested only in the pressure difference between 2 points along horizontal direction. So even if I do not take the parabolic shape, the answer would be same. So in fact it will take this type of shape, and here I am taking a little part of the liquid which is at a distance say x from axis, and this has a thickness dx, and this section we can take off area dA. Pressure here is say P, and pressure at position x is P, and pressure at position x plus dx is say P plus dA. And we are making FBD of this element while sitting on this rotating container. So this part should be in equilibrium. So from here, from left side, force due to pressure would be PdA. From this side, force due to pressure would be P plus dA into, P plus dP into dA. And this is also here. That should be P plus dP. And this is P plus dP into dA. And suppose mass of this part is dm. So a centrifugal force will act on this part, and the centrifugal force would be dm x omega square. With respect to container, everything is at rest, so this part is also at rest. So writing the equilibrium, so net force towards the left side is P plus dP into dA, and towards right is PdA plus dmx omega square. dm is the mass times the volume. dm is the density times the volume. So the density of the liquid is say rho, and the volume of this element would be dx into dA. So dm is rho into dx into dA, and then there is a x and there is a omega square. So this part was PdA that I had written here, and this centrifugal force is rho dx dA x omega square. From both sides you can see dA will get cancelled, and this P and P will also get cancelled. So what you will remain with, you will remain with on LHS with dA only, dP only, and on RHS we will have rho x omega square dx. So I got a differential equation of the variation of pressure along axis at a distance x from the axis of rotation as a dP by dx is equal to rho omega square x, and that I will be using here. Okay, so this I'll use. Now come here. So here also, this is also rotating. The axis of rotation is vertical and the liquid is horizontal, so I can apply the same result on any 2 points at horizontal level. So suppose the 2 points that I am taking are, this is point 1, and this point is just inside the tube 2, and between them this is a x, and here this element is dx. From here to here the pressure difference dP by dx got rho omega square x. So dP is equal to rho omega square x dx, and put the limits here. Here pressure is P1, and that P1 is basically P atm. Let me write it right now, P1 only. Pressure is P1, and here you see that this is L, this is H, and that would be L minus H, right? This is L minus H, and here there is a point 2, that is pressure is P2, and X is just L. So pressure difference that will come out, P2 minus P1 is equal to rho omega square x square by 2. So by 2 I'll put it here, and x square upper limit would be L square, lower limit is L minus H whole square, and this is rho omega square. I'll do that first, a square minus b square formula, or can keep it like this also. Suppose if I do the a square minus b square formula, so the difference would be h, and the sum will be 2L minus h, and divide by 2. And now I want to, suppose the velocity here, suppose this point is, see here, this point is 3. And here the velocity is v. So what I assume so far that this is obviously this orifice is very small, so the area of this is very large compared to this, so this is moving very slowly, so we have assumed this to be almost static, and that's why we applied all those things, because this was for a static liquid with respect to container. Now between 2 and 3, if I apply Bernoulli theorem, so from here to here, because of the pressure difference, the liquid is going out. So if I apply Bernoulli theorem between point 2 and 3, so the pressure difference here, the P2, the velocity at 2 is 0, just coming from 2 to 3, the pressure difference pushes that. So P2 minus P3, or you can go slowly and do properly. P2 plus kinetic is 0 here, plus same level, we can assume potential to be 0 here. Here potential energy is P3, sorry, pressure energy is P3. Kinetic energy is half rho v square, gravitational potential is 0. So P2 minus P3 is half rho v square, right? And P1, this is open, so P1 is P atm, and this is also open, so P3 is also P atm. P1, P3 are equal, so P2 minus P1 is equal to P2 minus P3. So in both equation, the RHS will also be equal. So if I go to this side, so I can write half rho v square, that was RHS of equation 2, and that will be equal to the RHS of equation 1. What is that? Rho omega square H, rho omega square H into 2L minus H. 2L minus H by 2. So we will be omega, we can take outside, omega rho H 2L minus H, and in fact this rho will also be, so that will be our answer. So that will be the velocity of efflux from the orifice, right?